In any classification, there's a lot of confusion. There's usually the introduction of terminology which at first doesn't make much sense. Looking at carbonates, we're looking at a system which is much more complex than a simple reference back to physical energy levels in the environment of deposition. In carbonates, there are two main classification systems. They've been modified, but the two primary sources are the Dunham classification or the Folk classification. Dunham's classification sets up categories in carbonate rocks based on their original depositional textures. There are three levels of observation at the top level of this classification. Were the grains mud supported? Were the grains grain supported? Or were the grains bound together by some sort of organic or inorganic cement at the time of deposition? That third group we can think of as biocohesively attached sediments. Folk's classification also describes the different types of grains, but it focuses in on the components, which Folk calls alchems, and the type of matrix or cement, micrite or sparite. Today, most people working with core or trying to move from the modern depositional setting into ancient depositional settings tend to favour Dunham's classification. It's easily transferable from the Holocene environment and unconsolidated sediments into ancient consolidated sedimentary rocks. Folk's system, as we'll see shortly, requires differentiation of things like micrite from spar. Now, spar is not a depositional feature, so it's more problematic moving from the Holocene unconsolidated carbonate sediment classification into the ancient using Folk's. It's much better suited to ancient rocks where you have a standard petrographic microscope available. All of these systems of classification, we're trying to organise what is very complex sets of information preserved in those rocks to reveal understandable relationships and patterns. We're trying to give us a framework for our knowledge. There is an underlying proviso in any classification of carbonates or any other type of scientific classification. We may oversimplify the boxes into which we place what we're classifying. So always think about, am I oversimplifying the interpretation based on this classification? What level of modifications was there going from the surface to the subsurface and then back up into the surface when we look at carbonate sediments reacting to those different hydrological and hydrogeochemical overprints? Okay, so let's start off with Folk's classification. This is a picture of Bob Folk. When I was on the faculty of the University of Texas in Austin, I had an office next to Folk's. The guy was brilliant. He was a magnificent mentor for me in my junior years as a professor. Folk published this classification back in 1962. It has three parts, what he calls allochemical rocks, orthochemical rocks, and autochthonous rocks. We've already talked a number of times about allo versus auto. Allochemical is transported, autochthonous is bound together. So allochemical rocks are formed of different types of grains or allochems that are out of place. They've been moved in the depositional basin. Those grains can be surrounded by either micrite or cement. Combining those two features in allochemical rocks, we come up with a sample name. We can have biosparite, which contains fossils, and a sparry intergrain matrix. If it's mud, we have a biomicrite. Likewise, we have oosparite, oomicrite, or if it's colloidal or pellets, pellsparite and pellmicrite. Orthochemical components are those components or orthochems that are crystallized or precipitated in place. This encompasses features that have a strong level of automicrite, microcrystalline carbonate mud, in place. It also, as we'll see later, encompasses the notion of micarbs in chalks as they're buried into the shallow subsurface. Autochthonous rocks are rocks that are made of material that's formed entirely in situ. Typically, we're talking about some sort of reefal or biocohesive structure. That's the first level of classification, where he's looking at the nature of the rocks in terms of their allochems, in terms of whether they're formed in situ as autochthonous, or whether there's some level of recrystallization as we go from a micrite to a dysmicrite. Then we have the textural name, the lower part of this figure. It highlights sorting and rounding to illustrate a spectrum of environments where we have different energy conditions at the time of deposition. Folk's premise was that the gradual transition from muddy to grainy deposits represents a gradation from relatively low energy to progressively higher energy accumulations. But remember that we also have this notion of how did that micrite form? Automicrite versus allomicrite. With Folk's classification, we typically combine textural terms We use the term where we have more than 2/3 lime mud matrix, subequal spar and lime mud, or 2/3 lime spar cement. He adds this concept where we have grain dominated with lime spar cements, the level of sorting and the level of abrasion and rounding into the name. So we can have a sparse biomicrite or a well-sorted and rounded biosparite as an indication of energy levels in the environment of deposition. It's fairly easy to use. Its biggest limitation is that we need a microscope to identify components. The other limitation is that it's a bit awkward when we try to apply it to modern sediments because we don't typically have spar as a depositional aspect of modern carbonate sediments. It's also not very useful in describing different types of autochthonous reef rocks, and differentiating between micrite as a sediment versus micrite as a cement, that is allo versus automicrite, can be quite problematic. Then we have Dunham's classification. This is probably the most widespread classification in use today, where Dunham looks at that interaction of physical energy and organic binding. At its simplest, the uppermost level of this classification breaks out the nature of the textual framework between particles. So we say depositional texture recognized, depositional texture not recognized. In other words, a heavily over-crystallized, over-printed texture we call a crystalline carbonate. A lot of dolomite spar would be classified as a dolomitic crystalline carbonate. The next level down in Dunham's classification is, were the original components bound together or not bound together? Were they biocohesive? If they were bound together, Dunham's term, the general term, is boundstone. If they were not bound together, the next level of differentiation comes at, does that specimen contain mud or does it lack mud? If it lacks mud and it's grain supported, it's a grainstone. If it contains mud, then we have to think about whether it's a grain-supported rock with mud in between the grain supports, which makes it a packstone, or if it's a mud-supported rock with more than 10% grains, it's a wacky stone, or if it's less than 10% grains and mud-supported, it's a mudstone. Dunham's schema, as it was originally defined, focuses in on the texture of the rock, with the major division between grain-supported and mud-supported fabrics. We then break it down into mud-supported rocks with more than 10% grains, waxstones, less than 10% grains, mudstone. If the rock was grain-supported and there was no depositional mud, it's a grainstone. If there was depositional mud, it's a packstone. This is quite an easy to apply, rather elegant system, easy to use both in the modern and the ancient, as it relies only on the textural components of the sediment and the rock. We don't need a microscope per se. We're not differentiating spar from non-spar. It's largely independent of interpretation, and it largely avoids a lot of the semantic issues that can come into play with diagenesis when we look at ancient rocks. Dunham's rock names are often modified with grain component prefixes such as oolitic grainstone or bryozoan crinoid grainstones. Sometimes people combine Folk's classification with Dunham's classification, so we might have a bio-oosparite grainstone combining terms coming from Folk and from Dunham. Let's have a look at the different styles of rock using Dunham's classification. We'll start off with mudstone, which is a mud-supported rock with less than 10% grains. Lime mudstones are typically made up of clay-sized carbonate particles. Much of that mud, as we saw in the previous discussions, comes from the disaggregation and the breakdown of calcareous hard parts, coming from the green alga or from the metazoan components, or in the case of the deep marine basin since the mid-Mesozoic, from the breakdown of the pelagic coccoliths. Mudstones in general, as both Folk and Dunham imply, tend to accumulate in relatively low energy areas, the lagoon, the distal four reef slope, or deeper water. But mudstones can also be found in higher energy environments where we have, for example, seagrass beds, and we see the breakdown of the organic material in the seagrass, and it leaves behind the mud that was captured in amongst the fronds of that seagrass. That type of capturing effect, as we said before, is a baffling effect, and we'll see a little later. It's called a bafflestone. The colour in most mudstones, dark or light, is primarily determined by its redox history. We'll get back into this when we look at carbonate diagenesis. Many muds are subject to recrystallization. There's a very common transition going from micrite to microspar in the burial environment, or micrite to minicarb, and we'll look at these in detail in the carbonate diagenesis section. Chalks are a good indication of this type of recrystallization process. The lower diagram is showing us a chalk from Ecophysk, which is a lower Paleocene coccolith chalk, When we take an up-close look at the Ecofist chalk reservoir, some of those calcite crystals have sharp euhedral outlines. They're not the original breakdown of the coccolith fine-grained material. They're breaking down into individual calcite crystals. Some of those crystals can merge and fuse and grow to create particles that are up to 6 microns across. These are the mini-carb particles. Even in a mudstone, we can preserve evidence of alteration. Most ancient lime mudstones are unstable. This is especially true in the platform, where they begin life as aragonite or high magnesium calcite, and they convert to calcite with burial. Remember, as we discussed in the mineralogy right at the start of this module, aragonite and magnesium calcite are metastable minerals. So as part of that conversion to low magnesium calcite, which is quite often a microsporium, that's a primary burial pathway for these aragonitic and high magnesium calcite minerals to reach the thermodynamic stability of low magnesium calcite. The other thing that happens here can be compaction. Quite often the porosity levels in a carbonate mud is quite high, up to 60 to 70%. But as that mud dewaters in the burial environment, if it's made up of fecal pellets, and modern carbonate muds in the Bahamian lagoons can be up to 67% fecal pellet mudstones, when we see their equivalents in ancient mudstones, they tend to be quite homogeneous micrites with few or no distinct peloids, a combination of both biotubation and compaction. That transition from an aragonitic or high magnesium calcite mudstone into a low magnesium calcite mudstone, and that associated loss of texture tied to biotubation and recrystallization, is an indication of the high susceptibility of those early organic-rich grains to destruction or alteration during burial compaction. So mudstones don't stay stable in terms of their origins. There's a lot of alteration that takes place in a mudstone as it's buried. This leads back into our discussion of fractured carbonate reservoirs or fracking processes in carbonate mudstones when we get into the economic aspects of carbonate sediments much later in the course in the module dealing with the economic aspects. Wacky stones are carbonate rocks which contain grains that are matrix supported. And if there's more than 10% grains floating in a fine-grained matrix, that's our definition of a waxstone. Remember, we can have mud surrounding grains that are in grain-to-grain contact. That's a packstone. So this abundance of carbonate mud with mud separating grains floating in that mud is a feature of all waxstones. Like mudstones, these tend to be semi-protected, low-energy environments, lacking strong water agitation that allows the mixing of both mud and skeletal grains. But a lot of wacky stones are also the result of biotubation, the ploughing of the sediment by organisms feeding on that material and mixing more grainy layers with muddier layers as part of that biotubation process. The mud in a waxstone can originate from the breakdown of calcareous algae, from inorganic precipitation of calcium carbonate, and also from the breakdown of larger skeletal particles and fragments, as we saw with Alameda. Biotubation is also significant in most mudstones, where we get mixing of different sediment layers. We also get pellet creation. Pellets, if not cement, lose their pelletal shape. We can also have peloids in this environment. In general, when we see a waxstone, we take it to imply relatively calm water, disaggregation, and some restriction of grain-producing organisms in what is a relatively low-energy depositional setting. We could have some situations where the grains that are in the rock floating in mud are exceptionally large. We'll see a little later Embryon Cloven designated carbonates where more than 10% of the sediment grains are coarser than sand size, float stones. The next level in Dunham's classification are the packstones. This is a grain-supported rock. The grains are touching one another, but we've still got mud in between grains. It's muddy, but there's less clay-sized matrix present than grainy allochems in the rock. Typically, packstones are taken to indicate somewhat higher energy, moderate energy, warm water environments found in semi-protected lagoonal areas where there's a fair degree of bottom reworking. They may contain abundant pellets or peloids, indicating biotubation and also grain degradation by various endolithic and other organisms living in that moderate energy environment. We'll see a little later that most carbonate sedimentation is a sediment mosaic. These are not consistent beds. Packstones pass laterally in the waxstones into grainstones on a single depositional surface quite quickly, and we'll look at the controls on this in the next module where we deal with the geological aspects of carbonate sedimentation. Often with a carbonate sediment, we have to make an interpretive step here. When we look at a carbonate rock, we have to make the determination of what is the distribution of grains to finer grain material. Often looking at a weathered surface can give us a much better indication Here we've got fusulinids. This is from a Permian sample in Thailand, where we can see on that weathered surface a much clearer distribution of the nature of the coarser grain material to the finer grain material. We could call it a benthic 4am packstone, or we could call it a benthic 4am rudstone, because those grains are actually coarser than sand size. And we'll come back to rudstone a little later on. We have to ask ourselves, in our packstone, is it grain or mud dominated? This coexistence of grains and muds suggests, as we said, a deposition in a moderate energy environment, where the energy was high enough to produce and transport grains, but low enough to allow some mud to settle in the intergranular positions. Now, Lucia's classification, which I'm going to talk about in detail when we get into the economic aspects of carbonate reservoirs, Lucia's classification divides packstones into mud-dominated, where the pore spaces are totally filled with mud, and grain-dominated packstones, where some of the intergrain space is free of mud. It may be filled by spar or it may be open. That division between a mud-dominated or a grain-dominated packstone is an important one. It greatly influences the permeability when we're looking at ancient reservoir rocks. Here's some more examples. Here's an orbitulinid packstone, where you can see the coarse foraminiferal grains with a grain-dominated matrix. And here is a Cretaceous Elabra milliolded packstone, where the microspar has recrystallized from micrite in between the milliolded 4am grains in this particular lagoonal sample. There are some other things when we talk about packstone versus waxstone that we have to think about. One is compaction. When we form a waxstone, where the grains are floating in a finer grain mud, much of that mud is water rich. That original waxstone may record burrows of different layers. Maybe there were grainstone layers with mud interlayers. But we can also have a situation after biotubation. We can convert diagenetically a waxstone to a packstone purely by the effects of compaction. As we dewater those muds, we compress that sample, we push those grains, those allochems, into grain-to-grain contact. So we convert a depositional waxstone into a diagenetic packstone. If we have grains that are coarser than sand-sized in grain-to-grain contact, Embry and Clover modified Dunham's classification to call that type of carbonate a rudstone. Then we have the grainstones, where we have clean sand-sized grains in grain-to-grain contact. So a grainstones are detrital lime sand without mud at the time of deposition. Those grains, those allochems, can be shell fragments, ooids, peloids. The important thing is to call it a grainstone. They're in contact and they're self-supporting. Because they were open when the sediment was deposited, often with burial, the intergranular positions, the interstices, are filled with a post-depositional sparry calcite cement. Sometimes the grains can be fully micritized to form peloids. Other times the grains can preserve those micrite brines or envelopes, as we see in the lower sample in the Ooskell grainstone, where we preserve the micrite brines around the bivalve fragments. Grainstones can form in both cool and warm water settings. In cool water temperate settings, and we'll discuss this in detail in the next module, in cool water carbonate settings, we tend to see heterozoan skeletal sands composed of things like bryozoan, mollusks, and brachiopods. Whereas in tropical warm water settings, quite often the bioclasts are composed of skeletal material or ooids or peloids. Grainstones tend to form in higher energy environments, for example on shallow marine shoals, on tropical and temperate carbonate platforms and shelves, where the sediment is being worked or reworked by wave and tidal energy. They can also form in tidal bars and beaches. They can also form grainstone shoals behind reefs. In that type of situation, the grainstones form in the more protected low-energy lagoons. We can also have aggregated peloids called gravestones developing in that back reef environment. In general, we're talking about moderate to high energy environments, but the hydraulic significance will vary. It will also vary according to the level of biocohesion, as we'll talk about a little later. We can have high energy, grain productive, agitated environments, so energetic that mud just can't accumulate depositionally. Or grainstones can be deposited by currents that are dropping out the grains and bypassing the mud to other areas. For example, solitons, internal waves passing over the upper slope, can create grainstones from what was originally a carbonate waxstone or packstone. They can be the product of winnowing of previously deposited muddy sediments. In all of these carbonates, you need to look through the diagenetic curtain. That's Dunham's classification as it deals with mechanically deposited sediments. as we range from clean sands or grainstones down to the other end of the spectrum with mud-dominated mudstones. The next video chapter is going to look at the classification of biocohesive sediments, boundstones.